Hello Math 2 Extended, I am Mrs. Bricky and this video is for Unit 9, Lesson 2. We'll be talking about quadratic functions in standard form. So standard form of a quadratic function is the form where we have ax squared plus bx plus c. So we've got each of the terms with their set power of x. Last time we focused on intercept form, which is the factored form of a quadratic function. So standard form doesn't directly give us much information about the parabola, though if you think about subbing in 0, it's very easy to sub in 0 here, and we get that the y-intercept is c. So when you sub in 0 for x, the only term left is that last constant term c. So definitely the standard form of a parabola reveals to us the y-intercept. But unfortunately, knowing the y-intercept doesn't really tell you a whole lot about the parabola. For example, if you look at my beautiful picture right here, every single one of those parabolas has exactly the same y-intercept. So you can see that knowing the y-intercept just is not telling us that much about the parabola. And in fact, there's an infinite number of parabolas that have that same y-intercept. Today we're going to learn two different ways for finding the vertex of a parabola if the function is given to us in standard form. One of them is going to be converting the function straight into vertex form via completing the square. So we've talked about completing the square before as a method of solving equations, but now we're going to talk about it as a method for converting the function into vertex form. So the process will feel similar but slightly different than solving. And then the second way is that we're going to calculate the location of the vertex using the axis of symmetry and some equations. All right, so let's start by seeing how we can use completing the square to convert the function from standard form, where we have a list of 3 terms, into vertex form, which reveals to us the location of the vertex. So we're going to start with this first equation. It is y equals x squared minus 6x plus 4. Now, before, when we were using completing the square as a method of solving, we would... Let me see, if this was our equation, for example, we would get the 4 out of the way by subtracting it to the other side, you might recall. But as we're working with a function and using completing square, you might notice that like this side of the equation is the y, and we kind of want to keep that y by itself. So instead of subtracting the 4 and moving it to the other side of the equation, I'm just going to kind of shift it over out of the way a little bit and just kind of let it hang out for a second while I think about the other two terms. So you might remember that when we were solving, we would have these 2 terms, and we would be thinking about like what number do we want to add so that we can factor this as a perfect square trinomial. And that number that we need to add, it's like half of this number, but then I have to square it because that -3, for example, gets multiplied by itself. So I would add 9 to both sides when I was using this method of solving equations. But this is going to be a little bit different. We definitely do want to add 9. Like we are focusing on these terms, and we do decide just like before that we want it to be an x minus 3 squared. Well, an x minus 3 squared requires that we have a 9 here, and we don't have a 9. We have a 4. So we put that 9 there that we wanted, and we think about completing a square with these 3 terms, but then and this is a little bit different. Before we added 9 to both sides of our equation. Now we're going to add 9 and subtract 9 on the same side. Now that's my 9 didn't look very good. That's the same net effect as if I added 0. If I add 9 and I subtract 9, that's the same as adding 0. So it's not changing the value of that function. It's not changing the function itself. It's just changing the form of the function. So I put 9 with the x squared minus 6x so that I can factor it as that perfect square trinomial. And then these two terms can combine, and we can, combine them to be a -5. And so that is our vertex form of our function. That means that if I wanted to graph this function, it has a vertex at the point 3, -5. So that's called completing the square. But this time, instead of completing the square to solve an equation, we're completing the square to turn it into vertex form. Okay, so that's a little bit tricky, but this idea of adding 0, it's pretty handy sometimes in math when we want to change the form of the function. Let's try another one. Now, this one is a little bit different because this one has a coefficient of 3. So we are going to, again, we're going to kind of set that 81 to the side for a minute. It's still there. It's still plus 81, but we're just going to kind of move it out of our way for a second. And so we're going to focus on these two terms, and we're going to factor the 3 out because you can see that both the 3x squared and the -30x are definitely have a factor of 3 in them. So we can factor out that 3, and that leaves us with an x squared minus 10x. Now this is where we're going to complete the square. We're going to focus right here. What constant do we need to add here so that we can factor that x squared minus 10x into a perfect, into a binomial squared? So we want to create a perfect square trinomial here. So we have x squared minus 10x. Well, half of that minus 10x is a -5. And if we square a -5, we get 25. So we're going to add 25. Now, adding the 25 there allows us to write that perfect square trinomial as an x minus 5. Wow, squared. I do not know why that turned into a third power. Okay, so I wrote a plus 25, but when I wrote a plus 25 right there, I didn't actually add 25 to the function. Because of that location of that 25, I actually added 75 into my equation because the location of that 25 is multiplied by 3. So that is the same as adding 75. So to keep my equation in balance, I need to subtract 75. And so now I can finish up my vertex form of my equation by combining these two together. A -75 plus 81 is 6. And then let's not forget about our 3 that we had, our stretch factor of 3. So that's the vertex form of our function. It's 3 times x minus 5 squared plus 6. So that means that this parabola has a vertex at 5, 6. Okay, so it's pretty challenging, I think, when you have that coefficient to deal with. And I thought, these kids, man, they're so freaking smart. So let's try a really tricky one just for funs. Okay, so my coefficient now is going to be 1/2. We are going to try to complete the square with the coefficient of 1/2. So again, we're going to just kick that 55 halves out of the way. We just want it out of the way for a minute. It's still there. We don't want to forget about it, but we just need it out of the way for a second. So we are going to think about how to factor out a half from these two terms. So I'm going to put my 1/2 here. And obviously, from that first term, if I factor out a half, I have an x squared. But from the second factor, if that second term, if I factor out a 1/2, I need to put a number here with the x so that if I times it by a half, it gives me a 7x. So what I actually need here is a 14x. So think about that for a second. Think about if that makes sense. If we distribute that 1/2, will we have the two terms that I highlighted in blue? A 1/2 x squared and a 7x. And I think hopefully you can see that we would. So we've factored out that 1/2. And now we are just thinking about what do we need to put, what constant do we need to put right here so that when we can write that trinomial as a binomial squared. Well, half of 14 is 7, and 7 squared is 49, so we are going to be adding a 49. Woo. Now I wrote plus 49, but I didn't actually add 49 to my equation because the 49 is inside of a group that has been multiplied or is being multiplied by a half. So I actually added 49 halves to this equation. So that's what I need to subtract to keep the equation in balance so that I'm not changing its value. So I added 49 halves, and now I need to subtract 49 halves so that I have a net effect of adding 0. I'm sorry that my 9s are so weird today. All right, so we are going to finish up writing our function in vertex form now. This is a perfect square trinomial. We can write it as an x plus 7 squared. And then our constant over here at the end, I have a negative 49 halves, and I'm adding 55 halves to it. And so that gives me actually the number 3. So this parabola, in standard form, it looks all funky. But in vertex form, we can see that the vertex is at negative 7, 3. So that's a very nice vertex. The stretch factor of 1/2 is sometimes challenging to graph, but we're not graphing it. We just found the vertex and we wrote the function in vertex form. Okay, so in class we talked about looking at these equations that we have just been working with and trying to decide a way to calculate this h at the vertex that I have highlighted in yellow using the coefficients of the standard form equation. So if you want to pause the video, and here's a couple more examples, if you want to pause the video and try to think about that, it's kind of cool to think about. But if not, I'm just going to go ahead in the video if you don't want to stop and think about it. So the second way that I'm going to teach you for converting the function into vertex form, or for locating the vertex of a quadratic function that's in standard form, is to use the axis of symmetry. So for a quadratic function that's in standard form, the axis of symmetry is a vertical line, and we can calculate it. X is equal to negative b over 2a. So that will tell you that sort of that invisible line that cuts that parabola into two equal parts. So once you know the axis of symmetry, you have the x value of the vertex. To get the y value of the vertex, you just sub that negative b over 2a, that number that you've calculated, into the original function. So let's try that process out. Here is our first function, f of x is equal to x squared minus 10x plus 13. So you can see that's not a factorable quadratic function. So first, let's calculate the axis of symmetry. The a, b, and c are the same as what we used with the quadratic formula in the past. Our b here is negative 10, and our c value is 13. So the axis of symmetry is the opposite of negative 10, so that's a positive 10 divided by 2 times 1. That is an x value of 5. So we know that our axis of symmetry is at 5, the x value 5, x equals 5. That gives us the x value of the vertex. So in order to find the vertex, we need to sub that x value in. So that that would be 5 squared minus 10 times 5 plus 13. So that gives us, let's see, what is that, negative 12? Let me just double check so I don't make a whole video with a bad mistake. Negative 12. So if I maybe put my vertex right here, that would be negative 12. Okay, so we have our vertex. You can see from the a value being positive that this parabola is going to open upward. Let's find the y-intercept by subbing in 0. When we sub in 0, we get 0 squared minus 10 times 0 plus 13. So that is an intercept, a y-intercept of 13. So we've got this y-intercept here. Our vertex is down there. Our parabola looks like this, sort of. Okay, I kind of missed that y-intercept, but you get the idea. Okay, that's 5 and negative 12. Okay, so the extreme value of this is a minimum value of negative 12. And so we can now write the equation of that function in vertex form because we have the vertex. So it is x minus 5 squared minus 12. Our a value here of 1 is the same as the a value in vertex form, so you don't need that 1 written there, but it is just a stretch factor of 1. And again, I'm not looking at the graph to write that vertex form down. I mean, I guess you could, but I'm really just, using the vertex. Okay, so that is the process of using the axis of symmetry to locate the vertex of the parabola. Let's try that one more time with a little bit more complicated function. You can see from the a value here that this parabola is going to open downward with that stretch factor of negative 3. Let's find our axis of symmetry. So the axis of symmetry is going to be x equals, so it's the opposite of our b value. So that's going to be negative 18, which is positive 18, divided by 2 times our a value. So that is negative 3. And so now that we know that the vertex is located at an x value of negative 3, we can calculate the y value by subbing in that x value. My battery must be getting low on my pen or my computer because my numbers are getting hard to write. And that usually means that my battery is getting low. Okay, when I calculated that, I got 8. So our vertex is at negative 3, 8. Our y-intercept is at negative 19. Again, we can calculate that by subbing in 0, but then those first 2 terms are just 0. So our y-intercept is that constant term, negative 19. Okay, I want to make a quick sketch of this, and then we'll write the equation in vertex form. Our vertex is negative 3, 8. So here it is. That's an 8, and that's a negative 3. And don't be bothered by not having a coordinate plane here or not having tick marks. You just label it, and it's perfect. Our y-intercept is negative 19. It is way down here. Whoa. Okay, there's my parabola. Next you might be wondering, what are these x-intercepts? That's what we're going to focus on next class. So we're not going to worry about those today. All right, so let's write this function in vertex form. It's going to have the same a value right here. That stretch factor is negative 3. And now we're going to use our vertex to write the vertex form. This is going to be an x plus 3, and then it's going to be a plus 8. So we've got a parabola stretched by a factor of -3 that has a vertex at -3, 8. That is, wow, that is good handwriting. That is perfect. Equation in vertex form. Okay, let's see what we got coming up. Oh, again. Okay, this one has fractions. Don't be afraid of fractions. They are just numbers. All right, x equals, we're going to find the axis of symmetry first. So it's the opposite of our b value. So that's going to be 5/6 divided by 2 times our a value. Now, remember when we were working on trig, we said that you can also cancel out division. So I can see that I have sixths, like divide by 6 on top and divide by 6 on the bottom. I can cancel that out. So that means my axis of symmetry is at 5/2. If you have to stay sane, you can use 2.5. I'm going to leave mine in fraction form. So we know that the vertex has an x value of 5/2. We need to find the y value. We're going to find that by subbing in. And I am definitely going to use my calculator to Ooh, that's a nice 6. Definitely going to use my calculator to calculate this y value. So let me type that into my calculator. 1/6 of 5/2 squared minus 5/6 of times by 5/2. Whoops. I just lost all the stuff I just typed in. I am sure you can feel my pain. It's happened to all of us. Okay, let's try that again. 1/6 times 5/2 squared minus 5/6 time. They should have an undo button on calculators like they do on computers where you're like, just kidding, I didn't mean to hit that. Okay, I just calculated it, and the y value is -121 over 24. In decimals, that is around -5, really close to -5. Okay, so our y-intercept you can actually see on that standard form. If we sub in 0, we're going to get back -4. And we are ready to graph this thing. So our vertex is at positive 5/2, -121/24. I declare that to be right here. Our y-intercept is actually at -4 right here. Like this is around -5. This is around -4. This is like the most widest, fattest parabola you ever saw. There it is. That doesn't even look like the vertex. That looks more like the vertex. Our sketches can't all be perfect. It's good enough. Okay, let's see. So this is 5/2, -121 over 24. Wow, the 2's are not working well with the current battery situation. Okay, so our y-intercept is -4. You can see the x-intercepts. One is positive, one is negative. We'll work on finding those next class. Our last job is to write this equation in vertex form. So we get y is equal to 1/6. So remember, the a value is the a value is the a value. 1/6 multiplied by something squared. The something is going to be an x minus 5/2. And then the y value at the vertex, -121 over 24. That's the fanciest parabola you ever wrote. Okay, all right. I think we're really close to being done. You can probably do most of the assignment based on those examples, but I just need to talk about one last little idea. We did an activity in class. I'll show you. Boom, it's right here. This activity that we did in class was a graded activity. So if you were gone from class that day, you need to do this. You can come and pick up the papers and do it. It really doesn't take very long, but it's great to help you develop some good skills thinking about parabolas. And it is just creating a function that has some given constraints. So we're going to just be creating a couple of quadratic functions. So our first one is if we have some known intercepts or we have some information about the intercepts. I want to create a quadratic function that has two positive x-intercepts and a negative y-intercept. I think the first thing you should do is draw a picture of what that looks like. If I have two positive x-intercepts and a negative y-intercept, can you see the parabola? Remember, it's symmetric, so we know that the vertex is going to be, over here between these two intercepts. So we've got this parabola, it looks something like this. So let's just pick a number. Like maybe this is 2 and this is, I don't know, how about 6? We've got a 2 and we've got a 6. If we know the x-intercepts, the most logical form to write the function in would be intercept form. I can see from my sketch that I drew that in order to get that negative y-intercept, my parabola has to open downward. So we're going to put a negative here for opening downward. And then my two factors are x minus 2 and x minus 6. So I chose to write this function in intercept form. Now, just to verify that I do have a negative y-intercept, let's sub in 0 for x and just check that we have what we want. And it looks like that would give us a y-intercept of negative 12. So we are good to go. That is a negative y-intercept. So here's our function. And, I just picked 2 and 6. It doesn't say what number they are. It just says they have to be positive. So I'm just building, something that fits those constraints. All right, let's do one more example. Create a quadratic function whose axis of symmetry enters quadrant 2 and whose range includes only positive numbers. So my axis of symmetry has to enter quadrant 2. That means my axis of symmetry is over here on this side. Remember, the numbering is 1, 2, 3, 4, like rotating counterclockwise. Okay, so we've got the right axis of symmetry now. You could pick what value you want for that. Maybe let's make it something fancy. Negative 13, lucky 13. Okay, so the next constraint we have is that the range can include only positive numbers. So that means my vertex has to be positive and my parabola has to open upward. Otherwise, the range will include negative numbers. So let's see, that point, I declared the x value to be negative 13. Let's declare the y value to be 7. So let's see, now we can write our equation. Y is equal to, I could put a stretch value if I want, 2. As long as that's not a negative stretch value so that the parabola opens upward, we'll be good. Now, because I sort of wrote down the vertex there, vertex form is the natural choice for writing this function's equation. And so here it is. Now, again, there's no necessary reason that I put a 2 there. I just felt like it. And as long as you didn't do a negative stretch, it would be fine. You could do a stretch of 1,000 if you want, and it would be fine. Okay, so that's the kind of thing you'll have to do on the activity if you were gone in class that you missed. So let me know if you need that, and that is it for the Lesson 2 video. Let me know if you have any questions. Thanks a lot.